Okay, so the first thing that you need to do when you're powering a DC motor is considering a power supply. What you need to do first is look for AC to DC power supply, converting 120 volt AC to the desired voltage that we need for our motors. In our case, it's 12 volts. Also, we have to consider like parallel connections of motors. Since our motors are actually draw up to 6 amps continuously, we need to supply at least 12 amps of current, since we are running at least, like at most, two motors in parallel. So that means that we pick a power supply called the meanwhile 12 volt 28 amp power supply to supply our motors for our robot. Okay, so to control this robot, we use an H bridge, in which if you turn on this MOSFET and this right here, you create a higher potential here than here, turning the motor one way. And likewise, if you turn this MOSFET on and this MOSFET on, you create a path going from here to here, and that would power the motor that way. These diodes right here are actually called flyback diodes, and they're used since when you switch from on to off, you need a path for the current to go. Since the motor is spinning, it doesn't want to stop right away, so if you don't provide a path for the current to go, it's going to end up a huge spike, and that could burn out the H bridge. Okay, so how do you choose one? It really depends on which motor you're using. In our case, we have our motors draw up to 6 amps, but we also have to consider a stall current, in which the motor draws more current at the beginning when it's starting to turn. And so we picked the Pololu 18 volt 15 amp motor driver. It's an H bridge that is rated to do 15 amps continuously without a heatsink. The supply voltage for this can go anywhere from 5 to 30 volts DC. The reason why it says 18 is because that's the recommended voltage for a battery, since there's fluctuations in the voltage. Also, if you look at the size of the Pololu motor driver, it's actually comparable to a quarter. And for these two output A and output B pins, we're actually connecting them to the 2 terminals of the DC motor. And the V plus right here is the power supply. Here's the ground. And your pulse width modulation signal goes into here. Minimum threshold voltage for logic high for this is actually listed as 3.5, but after testing in lab, we found it out to be about 2.4 volts. This is actually good because it will actually is compatible to the 3.3 volt output of the Arduino Bio. This direction pin controls the direction in which it is rotating. And there is also a 5 volt pin right here that can supply up to 20 milliamps, which you can use for a photo interrupter, which Tom is going to talk about.
Right, so now that we've got our motors spinning, we'd like to get some sort of feedback from them. And the most reliable way that we'd like to do this is we'd like to count the number of rotations. And so we can get, from this, we can count the rotations, we can get a position, and from the position we can get the speed if we have a concept of time. And then from there, I'm going to show you how to expand that sensing of just a position and a rotation count and a speed to getting the actual direction, completely independent of any intuition from signals that you have generated that might be telling the motor the direction. So to get just a speed or the fact that a motor is rotating, you're using, you can use a photo interrupter. It's a really simple circuit. There's a phototransistor and a photodiode, and this is a Sharp, one made by Sharp Microelectronics. It's 3 pins. You give it a VCC, you give it ground, and then it has a signal pin. And so we're going to put basically a gear in the way, it's called an optical chopper, that has spokes on it. And as it rotates, the spokes will interrupt the beam and then uninterrupt the beam and then interrupt it. And so if you know the number of spokes that you have, this will generate a square wave, and the frequency of that square wave is going to be relative to your speed. And each pulse will mean that the motor has rotated a certain number of angles. And this is independent of any, whether or not you are even driving the motor. You could twist the motor with your hand and get feedback from this that would be reliable. But using only one of these, we don't have any information about what direction the motor is moving in. So, and to hook this up to our Arduino boards, this is the line that we use is just attach interrupt. You give it the pin number, the function to run, and then the edge to catch. You can give it rising, falling, or just change, and it will catch both. Run this function, which we can use to update our position variable. So to get a direction out of this, if we add a second photo interrupter and we place them correctly, then we can get some additional information whenever the interrupt happens. So say we hook up, these are our photo interrupters, and here's our chopper wheel. We hook up number 1 to the interrupt, and the motor is spinning clockwise. When we catch the interrupt in motor 1, if we just read the output of the second photo interrupter, we'll see that it's been interrupted already, which means the motor is traveling this way. Otherwise, if it's moving the other direction, when 1 is interrupted, 2 has not been interrupted yet. And we can get that. And so using those two pieces of information, we can glean the direction of the motor from these two sensors. And the second function that will need to be added for this is, aside from attach interrupt, is just a simple digital read. The second one goes into the digital input pin, read the value, and that'll give you the direction. So then to get the speed that the motor is moving, if you want to compensate for having a load on the end, we need to test for the time, see how long it's taking between each pulse. And so the angular velocity is relative to the number of pulses that we're getting, and that's dependent on the number of probes that we have. So these two lines right here will do all the work for us. The millis function in an Arduino is the number of milliseconds since the board was activated. So we can get a change in time that here I have called D time. That is the total number of milliseconds the program has been running minus the current time, which is the time that we're tracking. And then we can update the current time by adding D time to what the old current time was. And then calculating the RPM, it's 1 over the spoke count, which will give us the number of pulses per rotation. And then divided by this change in time, which is in milliseconds, so this is the conversion to minutes, and that will give us rotations per minute for the speed of our motor. And so with two simple sensors, we can get all sorts of feedback, and this is completely independent of whether or not we're driving the motor, and we don't need any intuition about this. Someone could walk up and could force the motor in a direction, and it would get feedback that would be reliable as to the direction and how far the motor had gone. So this is, just in summary, we've talked to you about everything that's on this chart. Kake talked to you about the wireless transmission, the wireless communication, and the two boards. Ali talked to you about the joysticks up here and how they're all configured to work. Dan went in depth here on the H-bridge and the motor driver, and I've just talked to you about these two photo interrupter circuits, which are all put back into here. So if you have any questions, we'll take them now.
Portions from the class.
Yeah.
Seems like I've noticed quite a few number of people starting to use the Arduino board. I was just wondering what that draw is and how you
They're really, really modular and easy to use. And this file board that we're using is $25, and it comes with all sorts of I/O capabilities. There are the 14 digital input-output pins, 12 of which, 2 of them are reserved for serial communication. The other 12 are just general-purpose I/O. And then 8 10-bit analog to digital converters hooked up to 10 other pins. And one of the big draws of these is that they are really easy to configure. All of the analog input pins, for example, can be repurposed to be used as additional digital input-output pins, which we're actually going to have to do because we're one pin short without using one of them. But there's a simple piece of code you can write that will allow you to do input or output over analog input pins. So they're really simple to use, and there's a really big base of code out there.
All right, that was a good question. I have one quick question
Yeah.
for over time. You mentioned about programming through pin D3, is something that was selectable?
You can choose another one.
You can choose other pins for
Yeah.
your streaming
That's
programming?
a pin on the XP connection with the file, not the file.
Oh,
storage,
so it's
but
not,
yeah.
is it, so it's a pin on the
Yeah, there's
processor
an
itself?
extra, well, there are 8 extra pins on the XP.
And you can choose any one?
Yeah.
What's the advantage of that? I don't.
Well, the XB radio has 8 of its own digital input output pins, and so if you want to do, for our, this controller XB, we have 3 XBs, and our controller XB actually has to route a signal. It has to be able to communicate to the receiver and be reprogrammable by the computer, so we needed to use 2 of them. One of them to communicate over the wireless in this direction from the computer to it, and then a different one to use as output to the receiver. And the socket on the file has separate pins for all of those that can be redirected into the serial input and output pins on the file.
Okay.
So they're independent of the actual microcontroller's pins.
Okay, yes, I understand.
I'm not sure why you
Yeah,
would
it
need to
seems like
use-
if they would just dedicate that to programming, and the other ones would be configurable.
Right, well, and for this application that makes sense, but I think there are other applications for XP radios where you can use them with some other system where that having 8 input output pins would be helpful.
All right, good. Okay, thank you.